geometry? The area formula for a triangle? Are you serious? Alright, 1/2 pH, right? Alright, so how many times can you do that with different numbers for the same triangle and get the same answer? How many different times can I take 1/2 base times height in one triangle using a different B value, using a different H value, and still get the exact same area back? 3 different times. Okay? Because of this idea here. Okay? Base is B stands for base, right? Okay. Now, mentally, visually, a lot of you might think about base as being bottom, right? But it doesn't have to be the bottom. It's just the side that H is perpendicular to. H is an altitude. Goes from a vertex of your triangle perpendicular to the opposite side. So I've got these purple lines in here. These purple lines are the altitudes. Okay, they are the line that starts at a vertex and goes perpendicular to the opposite side. Now we're only interested in a formula for the dotted version or the dotted portion of those, right? Okay. So if I were to take out this gray triangle, cut it out, give it to you in front of you, gave you a tape measure and said measure the height of it. Most people maybe would put A, B on their desk, right there. Put this up in the air, point C up in the air, and measure from C straight down to D, and that would give you that distance, right? And that's the shortest distance from C to that side. And that would be your H, correct? Okay, so I can use that dotted line right there as H, and then if it's going to that side there would be B, correct? But can you take that exact same triangle and put that side on your desk? So rotate it, right? If that side's on my desk, wouldn't A be up in the air? I'm going to take my tape measure from A straight down to my desk, and that would be that length right there, correct? And that length would be another altitude, which could be H, let's call it H1. But what side is that going to? It could be that side, right? Let's call that B1. Are those two different H values and two different B values? Right? Okay. But now, H1 pairs with B1, it's always going to go to B1. H is always going to go to B. But there are two different values of B and H, but when I plug them, either of them, into this formula here, I should still get the same area back, right? And I can do that with the remaining altitudes. So what I want you to understand is that when you're finding the area of a triangle, there's a group of 3 of you doing this, all 3 of you might have different numbers. But when you calculate your area, all 3 of you better have the exact same area, right? Okay. Now, the reason there's really these purple lines here is because this should be true no matter what triangle I look at. Okay, so if I look at that triangle, it's an obtuse triangle because angle A here is bigger than 90 degrees. Now, if I wanted to use maybe this altitude as H, and this is the side or the base that it should pair with. Okay, that's what we talked about in geometry. If I wanted to use that as H, then obviously that, I think it's a little easier to see if that's the base that should go with, right? And then if I wanted to use that as H, call that H2, then this here would be the base that it goes with. Okay? Now, usually if I were to give you that gray triangle, most people are not going to think about using those outside altitudes, right? Okay? Most people are probably going to maybe put B1 on their desk and measure from A straight down to their desk. Okay? But there's absolutely nothing wrong with doing something like this. Let me clean this up a little bit. There's absolutely nothing wrong with this idea and saying, okay, there's my obtuse triangle. Let's say this side here is my desk. Would you not put, if that's in the air, would you not put your tape measure there and go straight down? And I'll tell you how to call that triangle off your desk. Does that make sense? So that would be your H. Okay. Now, what I want to get into, and just kind of rehashing that, was the reason for what I want to get into here. If we are talking about, let's say, any triangle, let's say this triangle here. Okay. Let's say that I've got interest, or maybe I've been provided this angle right there, theta. Let's say I know that angle. Okay. And I want to find the area of this triangle. Well, the area of the triangle you told me was 1/2 base times height, right? Okay. Now, if I know theta, I don't, in this picture, I don't know the height, right? If I'm looking at that triangle, just making in that orientation, maybe the best thing to do would be to try to figure out if I know that distance right there, right? I don't know it, but if that's h, and maybe I do know, maybe the the problem is providing me those two numbers, a and b. Okay, so I know those lengths. If I know those two lengths, now b is from a all the way to c, so that might not help me in this situation, but a certainly does help me in this situation in finding h. If I know a and I know theta, isn't it? If I look at theta, what side is this here for theta? Opposite. What side is this theta? Hypotenuse. So if I were to find h, and I know theta and I know a, can't I say sine of theta is equal to h over a? That make sense? And then the h for my altitude would equal a sine of theta, correct? That make sense, everybody? That would be my altitude. And in this situation, I know a, okay? If that's my altitude, could I then plug that h, that's my altitude, doesn't that mean it's that h right there in the formula? Okay? And what would be the base, that that altitude is being drawn to? It'd be segment AC, right? It'd be the bottom there, or we are defining that also as lowercase b, right? That would be that whole distance. So this is h. That's the altitude, and that's the base the altitude is being drawn to. So let's say area, instead of writing as 1/2 BH, let's say it's 1/2 base, which in this case is just this lowercase b. And then h, we just found out to be that thing right there, right? So let's put h in as a sine of theta. And if we use the commutative property to see this match up to the formula from the PDF here in a moment, we see that the area for a triangle is exactly the same thing as 1/2 AB sine theta. Okay? Now here's the thing. What does that mean? What does that formula allow us to do? And it allows us to find the area of any triangle if you know that angle there, and you know, oops, not that. If you know that angle, and you know the two sides up here of A and B that I have labeled, okay? So this, would you agree that this is a side? And that's an angle, and that's a side, right? You guys remember from geometry, we got side, angle, side. Okay, and we use side, angle, side a lot for different types of properties and theorems, postulates. But that orientation of one triangle is where you've got A being stuck between two known sides, right? The angle you know is stuck between two sides. So if I want to find the area of this, and GeoGebra is doing it, 20.64. So if you take your calculator out, okay, now it's saying that A here, I'm going to have to pull some stuff off the side here. A is 7.97 and B is 10.54. So if I say 1/2 times A, which is 7.97, times B, which is 10.54, and then times sine of this angle, which is the known angle that I knew, 29.41. Let's put that in. Now I got to make sure I'm in the right mode. Before I hit enter, I think I am. Yeah. And if I hit enter, it should give me the 20.64 number that we're getting. And now there's a little bit of rounding error. That's 20.62. This is 20.64 because that's one rounding to two decimal places, two decimal places, two decimal places. So there's quite a bit of rounding error being compounded in my calculation on my calculator that GeoGebra isn't having. But that allows you to find area without directly finding the height of the figure. Does that make sense? Okay. But the sine of that 29.41 multiplied by A is effectively inside the formula finding that height for you anyway. Does that make sense? Yeah. So what I want you to understand is that, and maybe you see this in a physics class, when you're in physics, you get all these types of formulas, right? They tell you to memorize them. What I want you to understand is a lot of those formulas are things like this, okay? Where it's a generic formula that you might have known from 7th grade math, where they just substitute convenient values, okay? Substituting H here as A sine theta develops a whole new formula. And we think it's another way to find the area of a triangle. It's not. It's still 1/2 base on height, right? Do you agree with that? Okay. And I'll show you some other formulas that we go through throughout the year that they're 7th grade, 6th grade formulas. But we just make these substitutions that develop maybe a little bit more of a complex-looking formula, okay? But they do and act the same exact way as other things, okay? So with that picture there, with that information, you should always be able to find the area of a triangle. 1/2 AB sine of theta, where A and B are the sides that are sandwiching the theta that you know. All right. So that's something I wanted to touch base on. It is in the PDF. It's the last question. I don't think I gave you any questions in your homework about it, but it is part of this section. Whether we use that very often, finding area of triangles is more of a freshman, sophomore course type procedure and practice. And really, once we move through this chapter, we won't do a whole lot of solving of triangles anymore in regards to finding their side lengths or finding their areas. So we're really not going to use that much more than just that section. That kind of makes sense? But I just wanted to let you know that there is more formulas or different formulas than what maybe you've seen in the past. There's a formula, maybe we'll get to it later, it's called Heron's formula for finding the area of a triangle. There's many different formulas for finding areas and volumes and surface areas that maybe you're not used to, okay? Because in geometry, in 7th, 8th, 9th grade math, we use the ones that are most maybe applicable, the ones that are most logical, most easily accessible, that type of thing. And we overlook the potential of those other ones, okay? So maybe this course will open our eyes to that. All right, so that gets us into this section 5.4, and we'll spend the bulk of today talking about this, and hopefully maybe in the next 2 or 3 days get all of 5.4 learned. But there's a lot of stuff going on here now, and I'm not a big fan of where they put it. I know why they do it, but I'm not a big fan of it right now. And basically they just present you all this information, say learn it. But I want you to understand why it's presented the way it is, where these values come from. And there's really a chapter 6 and chapter 7 information being wrapped up into the stuff of why it is what it is. Okay? But there's also some algebra, college algebra information here that we can kind of play off of and maybe open our eyes to. So what I'm about to tell you, what I'm about to show you, we will talk about again in a lot more depth. Okay? It'll make a whole lot more sense. But I don't want to give you information here and say, just know it, just learn it, because that's, I think, a problem. Okay? So when we talk about inverse functions, remember inverse functions undo another function, don't they? Like x squared and square root of x, they undo each other, right? So take an input value, run it through x squared, get an output. Take that output, run it through square root of x, and it should undo everything that x squared did and gets me back to my original input value, right? Okay? So if I take like 9, all right, let's do a smaller one. Let's say take 3, run it through x squared, what do you get? 9. Take 9, run it through square root of x, what do you get? 3. 3 gets you back to the original input of 3 that you started with, right? So they undo each other. Inverse sine, inverse cosine, inverse tangent are the exact same thing. Cosine, cosine, and tangent functions. Okay? And it's pretty easy to see which ones match up with which ones, right? Okay? But it's maybe not as easy to view and think about these functions without knowing what they look like graphically. Okay? We knew that in college algebra, when we dealt with something like, let's say, x squared, It looked like that, right? And that's a function because it passes what line test? Vertical line test, okay? But if I leave it that way, this thing fails the horizontal line test, right? So it's not 1-to-1, okay? Meaning that for every x value, there's one and only one y value, and for every y value, there's one and only one x value, okay? This thing would not be 1-to-1. So that would mean it doesn't have an inverse. Does that make sense? If it fails the horizontal line test, it does not have an inverse. But we know that x squared does have an inverse. But it has an inverse only if we do that. Only if we restrict the domain to saying x has got to be bigger than or equal to 0, then square root of x it can be created. Does that make sense? You remember doing that? Okay. So now that thing's 1-to-1. Well, that's the same thing that actually has to happen with the sine, cosine, and tangent functions. Okay. So I want to show you, and this is what I was talking about earlier. This will get into a whole lot more detail with this in the next chapter. So don't worry about copying any of this down. Just kind of watch, pay attention, and we can get the idea of where these numbers in that chart are coming from. If I graph sine of x, it looks like that. Okay, it's what we refer to as a sinusoidal. Sometimes maybe in a physics class you're talking about waves, right? Okay, but this is what we call a periodic function because it is doing the same thing over and over and over again, right? And we could determine the x distance in which this thing repeats itself over and over and over again. For this, it'd be 2 pi. Every 2 pi units on the x-axis, it repeats itself. So that repeating distance of 2 pi would be called the period. And we'll get into all that stuff later on. But what I want you to understand is that thing fails the what? Fails what test? Passes the vertical line test, right? But fails the horizontal line test. And it fails it a lot, right? Okay. So we're looking at that thing saying the sine function must not have an inverse. But if we look at our calculator, it does have an inverse. So we look at that PowerPoint, it does have an inverse. Okay. But we have to do something similar to what we did with x squared. We have to restrict the domain of that function so that it has an inverse. And the way we do that is we start thinking, okay, around 0, 0, can I start tracing this thing and highlighting maybe values that would allow this thing to pass the horizontal line test? So if I did this, let's say that I start here, okay, and I go there. And that's the only part of the green curve that I'm looking at. Does that red part pass the horizontal line test? Yeah. Okay. Because it hasn't passed through, it hasn't gone through, like right here, it goes through like 1/2, right? Y value 1/2. And nowhere else does it go back down to come through 1/2, right? So there's no two x values that have the same y value. So I keep doing this, and we would agree maybe that all those red values pass the horizontal line test, right? But if I do this, if I make the turn, that's the maximum point, right? If I make the turn, I start going down, decreasing now. Now does it start to fail the horizontal line test? Okay. So the infant that I saw when I started going down, I start failing. I don't want to include those. Okay. So right now, we've got those values being highlighted. We will pass the horizontal line test. Okay. And I know if I go any further over here, I'm going to fail. But will I pass if I add that? Will I pass if I add that? Pass if I add that, right? Okay. Now, what happens is that sine function is, remember the input values, okay? The input values of the sine function are angle measurements, right? Okay. So I'm going to put a value in here. I'm going to say x equals pi over 2. It puts that line in right there where I've got that dot, right? Okay. And what do you think this value over here would be? Negative pi. I'm putting a line in there. X equals negative pi over 2. And it puts that line right there. So do you see the x values that we have to use to restrict the domain of negative pi over 2 to positive pi over 2? Does that make sense, everybody? So if I do that, and I think I can do that by writing this. Negative pi over 2 less than x less than pi over 2. Can I do it? There we go. Let me clean these lines up. So that thing there is the restricting of the domain of the sine function that we have to use. Now, if that thing is 1-to-1, which it is, it should have an inverse, right? And the inverse of that thing is then the sine inverse. So what is the inverse? The inverse is when we flip this thing over the line, y equals x, right? Okay? Now it's kind of zoomed out here. It's kind of ugly, but if I flip over the line y equals x, the x's that are in this curve become the y's of the inverse, right? And the y's that are in this curve become the x's of the inverse. So here's the question. If I'm looking at this thing, oops, I want the grid to go there. If I'm looking at that thing, right now it's the sine function, okay? So the sine function, we put in an angle measurement here, right? And it spits out a ratio. So angle is your input, ratio is your output, right? This is an x value, that's kind of a y value, right? Does that make sense? Okay. Well, in the inverse then, when I write sine inverse, if the inputs and outputs, or the x's and y's, flip spots, what will be right here if I use sine inverse? You're putting a ratio in there now, right? So you're putting in a ratio, the comparison of two sides through division, and it should spit back the what that's associated with that ratio? An angle. Okay? So the sine function takes an angle and gives you back the ratio of sides that are stuck to it, right? The inverse inputs a ratio and spits back the angle that's always stuck with that ratio. Okay? But it's only going to do that for some angles. Okay? It's not going to give back a series of values that we need to think about. So for instance, let's say I type in sine inverse of some ratio. I will never get back maybe an angle like 210 degrees. And the reason for that is, think about these values right here. These values of the sine function has a domain, look at these x values, of negative pi over 2, comma pi over 2. Would you agree with that? That's the domain values here. Or if you want to think about it in degrees, it'd be negative 90 degrees to positive 90 degrees, right? The range for the sine function of your y values, they go from negative 1 to 1. Okay? Well, when I do the inverse, doesn't the inverse flip-flop the domains and ranges? So the domain for this function here, the domain for the sine inverse, is going to be the range over here of the sine. Does that make sense? So this is
James.
negative 1 to 1. Siri she just recorded every single thing I said for like the last 10 minutes. And she didn't really know, she doesn't know what to do. So the range then for the sine inverse is the domain of the sine, right? Does that make sense? So this is negative 90 degrees to positive 90 degrees, or negative pi over 2 to pi over 2. So the range is your outputs, right? So do you see that when I type sine inverse, I use that on my calculator. My calculator will never, ever, ever spit back an output number or a degree measurement or a radian measurement that is outside that. 210 is outside that, right? No matter what ratio you type in on your calculator, you will never, ever, ever, ever get your calculator spit back 210 with the sine inverse. However, we do know that there are times that I'll want to know about that 210, right? Okay. There is a ratio that exists with that 210, correct? Okay. So there will be times that we want to deal with that 210, but we then have to kind of learn what our calculator is providing us, understand this concept here, that this is why the calculator is providing what it is, what it's giving us, and then how do we adjust that number that is being provided to get the 210 that we're really interested in, okay? As we do some of these examples, I think it'll make a whole lot more sense. But I really, really, really hate giving you this chart and saying memorize that chart. So I think that's a terrible thing to do, okay? But you see where that domain and that range may become from the sine inverse, okay? The cosine inverse is developed in a very similar fashion, okay? The cosine inverse actually looks like, I don't have it up there anymore, it looks like the sine function. It's just translated, a horizontal shift, basically pi over 2 units to the right. Okay? So it's still that same exact way. Tangent looks a little bit different, but that's where all those things come from. Now, I don't know what happened when I input this into the PDF, but these black smudges are pi's. So that's pi, negative pi, pi, negative pi or 2, pi or 2, and I don't know why 2. Now, the old world kind of terminology for inverse sine, inverse cosine, inverse tangent are arc sine, arc cosine, and arc tangent. Okay? So that thing right there means the exact same thing as that. And that's where if you take the ACT, the end of the ACT a lot of times has, here, find the arc sine of, arc cosine of tangent. Well, that's just kind of stacking a bunch of sine, inverse, cosine, inverse together, so it's asking those types of questions. Does that make sense? Tomorrow we'll get into some examples of how to use this.